So let's take a look at that first, and then if you're interested, we can then move on to the inverse functions. That'll be if we still have other students in the class, but for now we'll focus on the expos and log stuff. So
Okay.
was there anything from exponentials and log diffs that were specifically challenging?
Yeah. There was one question. Could you give me a second? I'll just bring my textbook.
Yeah, no worries.
Okay, one of the questions. I had a bit of trouble with one of the questions. Can I say the question or?
Yeah.
Okay. Tangent to the curve y equals to.
Oh, it's not on the. Is it from the textbook or is it from?
It's from textbook.
Yeah, let me know what text. So which one is it?
The Jacaranda.
Oh, Jacaranda. Yeah, okay, I've got one. Cool. Jacaranda 3.4. And whereabouts in that?
Chapter 5.7.
5.7.
Yeah.
Is there a page
The
number?
last question. 337.
337. Thank you. 37.
Question 11.
Question 11. Tangent to curve at x equals n intersects at there. Calculate n. So basically to say, where should I take this tangent such that the tangent will cut at x equals that? Okay.
Yeah, I did solve it, but I did overthink it quite a bit. So the solution is all over the place.
Sure.
I did get the right solution.
So the solution was just kind of messy. You did end up getting it, although you're not too clear as to how that's worked, or would you like more so, I guess, looking for a more straightforward approach to it?
Yeah.
Yeah, sure. So this is definitely a CAS thing. You can tell from the decimals, even though they don't necessarily say CAS. I'm going to assume they meant CAS for this.
Oh yeah, it's technology active, so yeah.
Oh yeah, it is too. There's a heading for it. Nice. So you got this TI Nspire CAS, yeah?
Yep.
Cool. Tangent line function is a nice little thing. It works not only for if you know the x value, but also works if you don't know the x value for which you want to find your tangent at. So one of the things you can do that's pretty neat is you can get a fully generic version of the tangent line for any value of x. In this case, they've used x equals n, just some point along the tangent line. Having done that, what we now have is a generic y equals mx plus c, even though it doesn't look like it at all. That'll be your mx, and that'll be your plus c, because you can tell that's the thing that's got the x coefficient there.
Yeah.
Now, that's now a linear, basically, at that point. We're told that linear needs to intersect the x-axis at that decimal spot.
Yep.
Intersecting the x-axis, that's just an x-intercept. So in other words, let y equal 0 and solve for x in this case here. So we just grab the whole thing, let it equal 0, solve for, actually it's not even solving for x, it's solving for n under the condition of x equals 0.3521. So we set x as our 0.3521. I'm hoping we get a nice number. Yeah, so basically n is 2 in that case.
We are told to give it in integer form, so yeah, 2.
Yeah. That's how I go
Yeah, I
about
guess
this.
I was confused about how to do it on the calculator.
Sure,
I've done
okay.
most of it by hand.
Oh yeah. Well, yeah, by hand you can imagine. I mean, I'm just looking at this generic tangent line here. That's pretty intense to try and get to that.
Yeah.
As far as what else would you possibly do? You've got the point that it has to go through. Point. Yeah, so you could potentially do. I have something similar for the tangent line solution set. When you have 2 points, you can work a bit of magic with it by finding out where that other point would be. Let me just pull up an example of that. It'll be a lot
Can
easier.
we work on a little bit on the tangent line stuff? I'm not really sure how to use
Yeah, sure. So let me pull up some work on that, and we can go through the code.
could you give me a second? I'll just bring my calculator. I think I left it in the other room.
Yeah, all good.
Uh,
Cool. So as far as doing that like by hand, the closest example I would have would be this here. So you have the generic point. They had M, we had A, and we were told it passes through the origin. In this example, in the example on the Jacaranda book, it was 0.35, 0. So it's still fundamentally just point. One of them is known, one of them is generic, and we have our function. So the way you would start going about that by hand is first define those 2 points. So we had the origin here. You would have the 0.35 there instead. And then you'd have m, comma, natural log 2m, whatever it was in the log there. That'll give you your second generic point. Now, from there, we've got to remember when it comes to tangent lines, you need gradient and you need point, basically, or even more simply, the y-intercept. That'll get you your linear, the whole thing. Now, in this case, we actually have 2 points, so we're already +1 on what we need for the linear itself. All that's left is now how do we get the gradient of our linear? There's 2 ways you can get gradient. The basic version is just f dash. That's pretty much always available to you no matter what. And f dash is super easy, right? Just diff whatever you've got. Even in the example you gave me, diffing that log shouldn't have been anything too challenging there. That gets you one expression for gradient because derivative is directly tied to gradient. Right, it's an expression of gradients. But because we have 2 points, we can do it another way as well. It's linear between 2 points, rise over run. And so what we can essentially do is create a second version of our gradient formula and go from there. These 2 things are the same, or I guess more specifically these 2, because you've got to have the x equals a in there, that generic point. And because they are both talking about the same thing, they can now be equated, thus finding the spot where they would, what that a value was, with a reminder that that a value is the x coordinate of your generic point. So in this example, it will be getting you that. Now that you have a, you have gradient, because both of these are gradients. You just chug it back into either which one. And, you can just use the gradient point formula with any of the points to then get the rest of the tangent line. Is that all fair enough?
Yeah. Yep.
Sweet. This will be a lot more similar for what you would get in a tech free. The tech active, obviously, you wouldn't really be too bothered doing any of that because you can just solve the full tangent line without going too crazy with things. But that'll be the closest thing there. Otherwise, it's probably not even worth looking at the most basic one. It's just here's function, here's where we're taking the tangent. The CAS just does that immediately for you. Did you ever have any trouble doing these by hand?
No.
Not really? Yeah. The next one that might be a step up of challenge is going to be when angles are related. It's probably easier than example 2 though, I would say, because angle stuff you should directly in your mind translate back to gradient, essentially, because tan theta will always get you gradient. They'll typically use one of the angles on the unit circle. If they don't, it's a tech active one, and you'll do it that way instead. Fundamentally, this is just another way of them giving you gradient information rather than point information. So again, if we think about basics of getting our tangent line, we need gradient and point. We have gradient. We now need to figure out how we're going to get the point. So first up, we'll convert that tan 45 into 1, so it's actually a gradient value rather than angle value. And the next thing we've got to do is figure out how we're going to make use of that to work our way back up to the point that we're taking our tangent at. Well, f dash x, all roads lead back to derivative, essentially. Take the derivative. This is gradient with respect to x, which for our case, because we're trying to find gradient at a point, that x value is going to be the x-coordinate of that point. We have our gradient, we have our derivative, smash them into each other, you get the x value for which you want to take your tangent at. We've got x, we've got gradient, all that's left is getting the y. The y is pretty trivial to get, just shoving it back into the original function. Point, gradient, and then rearrange how you like.
Okay.
Sweet. What you've got here is probably the hardest of the questions. Was there anything else that you came across that you'd want to have a look at? Like even if it is tangent related.
Yeah, one from 5.6.
From 5.6. Okay.
Yeah.
What question, sorry?
Question B. Question 5.66B.
5.66b. That?
Yeah.
Cool. Okay. dl d theta.
L is already given.
Yeah, we've got the whole function there. It's basically the same as f of x. There's nothing really too
Oh wait,
different.
I don't think that was the question. Wait, I think it was a different question. Oh yeah, it's C. I didn't really understand C.
C. So using the CAS to sketch that L graph, determine the maximum length of the wire. Yeah, so I imagine this will be very similar to the generic way we maximize functions, where you would, well, even sketching it, you'll probably find a turning point there in some domain. You got the domain from 0 to pi over 2 there. The CAS should just have the graphing tool to be able to do that. So I wonder what you're saying.
I tried to do it on the CAS. It's just, I think it's my view.
Okay. Maybe just quickly double check you're definitely in radians mode.
Yeah, I'm in radians.
Okay. 400 sine theta plus 200. So it's got quite a drastic vertical translation to it. So let's fix up our domain, 0 to pi over 2. Let's see, is there anything else I should be bothered about? Length of wire. Let's go with like 500 up here. That should surely... Yeah, it just disappeared. It's even taller than this, is it? Okay, so if you zoom all the way out, like I've got a window size of 900 here from 0 to pi over 2 on the X. Was your issue finding the graph on the CAS?
Yeah, I've set both of them to 1,000, and I don't see anything.
Both as in the max Y and the max X?
Yeah, I mean I've set the max maximum to 1,000, both of them.
Um,
0 to 1,000.
you've done so 0 to 1,000 in the y, and then 0 to pi over 2 in the x, or
No, 0 to 1,000.
yeah, do 0 to pi over 2 for the x, because you can see on the L function, it's got a domain 0 to pi over 2.
Oh, yeah.
0 to
Oh,
1,000,
I
yeah, you
didn't-
would be seeing this thing go rapidly changing very, very quickly. So that might be why it's just a mess.
I still don't see anything. It's
Oh, don't
it's
see
blank.
anything. Yeah, okay.
I-
Could you maybe hold up the CAS to your screen? I wonder if I can maybe see it.
It's quite out of focus.
Yeah. Well, you got it
Okay,
in a
that's
solve.
wait. I've defined it higher. Okay, I'll try and write this out.
Yeah, whatever function. It looks like you define it in the CAS. Maybe just on the calculator tab, just type in the function name and see if you get exactly what you expect it to look like. Because it seems like you've defined it
I'll
in the
just copy and
calculator
paste
tool, and then
this. Yeah. I'll just copy and paste it.
yeah.
Wait a minute, this is not. Oh, I've copied the wrong thing. Sorry.
Sure. Even like just generically speaking, you could even just create a fresh window, type up the function fresh again. My assumption is that something about the way the function's typed up is a bit busted. Perhaps for whatever reason, x might be defined as something, so you're getting a constant. It could be what else? What else could it be? It could even just be a typo in the way it was defined.
I'll just look at the textbook and write it out from there.
Yeah. I'll double check it as well. So 300 cos, whoops. 300 cos x plus 400. You're definitely using x's, yeah?
Yep.
Cool. Yeah, I don't know. But yeah, obviously once you've now got it on the screen, finding that maximum would just be a matter of going through the analyze graph. You would then have your maximum, of course, which I think I misclicked. Go to maximum. And so what we're expecting to have is the maximum occurring there, basically. So I guess all we're doing is trying to figure out why yours isn't showing up on the screen.
Oh, right, it's shown up. It showed up now.
Yeah, okay, it was probably just some typo, something weird going on there. If you send me like a photo of your, if you want me to try and debug it for you, you can send a photo of it later, and I'll basically just do it myself. But you'll probably spot it at some point if you look at it again, some little weird typo thing.
Okay.
But yeah, so from here it should be fairly trivial where you go from there, yeah? Because it's just saying find the value of theta, so that will be the x value there. Since we're replacing our x with theta, 2 decimal places, you're looking at 0.93 for that one.
Okay. Yep.
Oh, actually, so determine the maximum length as well. So yeah, you would also need the L value as well. So that'd be the y coordinate of 700 there.
Oh, okay. Yeah.
Sweet. Well, that's about it for the diff stuff.
Yeah, I think so. Yep.
Okay. So as far as the curriculum content for this Unit 1 and 2 one, it was going to be the inverse function stuff. So it should be a fairly self-contained little thing. Pretty much any time you're doing the inverse of a thing, you're pretty much doing every question the same way. You're going to start by swapping the x and the y's. You can do a little middle step in the middle where you're actually renaming it as the inverse function as you're doing the rearranging, or you can just do it at the end, up to you. Basically, all you're doing is swap the x and y, rearrange for the new y, and then finally rename it at the very end. As far as what that's actually achieving, basically you start with a function, and what you're doing is you're flipping it in the line y equals x. So it's a type of reflection, but not necessarily a reflection in the x or in the y axis. You're now reflecting along another line, the y equals x line. And they do that a fair bit in like spec related stuff as well, where you now have asymptotes that are not necessarily the x or the y asymptote. You start having equations which define what your asymptotes are. Like we're used to the hyperbola, which has your vertical and horizontal asymptotes. Specifically, we're doing the rectangular hyperbola. There are other types of hyperbolas that have different parameters to them, and part of what they do in spec is actually create the equations that define those asymptotes that they write along. But that's obviously not methods relevant, more so just giving you the premise of, yes, you can have, you can work with more than just the x and the y axis when it comes to transformation related stuff. So let's see a very quick example of how this works with a basic linear, right? F of x equals 4x plus 5. First things first, swap the x and the y. I've said input and output in my notes because, you know, in this case we have f of x and x, right? So it's sort of generic depending on what letters are being used in the function. So this is now going to look like this. You're literally just replacing every single x with f of x and every single f of x with x. From that point onwards, I personally will now rename that as f inverse, even if it is a little bit more lines. It's more mathematically sound, because in math algebra you can't necessarily just swap variables without declaring what you're actually doing. So maybe if you don't want to declare or rewrite this immediately, maybe you'll do at the top like inverse, and then that'll define exactly what you're doing underneath. They should know what you're doing. The question's worded in a way where you're supposed to be doing these things, but these are the little things that might push you just over the edge of a study score increase. And then, yeah, rearranging. I mean, this is just linear algebra. There's nothing too much to go on. Subtract the 5, divide the 4, and you now have your inverse function. You've essentially performed that reflection across the line y equals x. Any questions about the fundamentals so far? Cool. It therefore follows that the domain and range of the inverse function should be the flip of the domain and range of the original. Because one of the things you're doing, especially like in this step here where you're swapping the x and the y location, is reflecting in the line y equals x actually is the swapping of each x with the corresponding y. Like for instance, this y value is now an x value on the other graph. This x value is now a y value on the other graph. So you're effectively swapping the locations of the x's and the y's of each of the functions. So if your original function has any restrictions on its domain or range, then that will be reflected in the inverse by flipping it around. That's the gist of it, really. Where that starts coming into play is where you start having to do inverses of more complicated functions. These are functions that are many to one. Basically put, you can really only do the inverse of a function so long as it's one-to-one, because as soon as the function doubles back on itself and you try to flip in the line y equals x, what you get from doing that procedure is no longer a function, it's now a relation. So it's where you have those sort of sideways parabolas going on, which is why in this question example, the first thing they're trying to do is get you to make it a one-to-one function. Because if you don't have it as one-to-one, when you do that inverse, as I said, you don't actually get a function as your result. So a lot of the time, the first step is, as we see here, figure out how to make this a one-to-one. Now for quadratics, that's fairly trivial. If we can only control b, so the upper bound of this domain, what's probably the most straightforward way of converting this into a one-to-one function just by controlling b? Any thoughts?
Limiting the domain.
Yeah, limiting the domain. So b is the upper bound of that domain. When it comes to limiting it, what sort of things are we trying to consider? Like where's a natural spot to put the limit at?
Usually the origin.
So origin, with like the very basic quadratic, yeah. The quadratic has its turning point on the origin. This one's got a bit of transformations attached to it, so it will be located elsewhere from the origin. So basically what we mean by a one-to-one function is, does it pass the horizontal line test? Like if I were to draw a horizontal line anywhere on this graph, if it only ever intersects the graph once, then it's passed that test. So when it comes to the parabola, any given side of its turning point passes the horizontal line test. It's only when it reaches and then crosses over that turning point that suddenly things break. So if we have full reign of what we could do as far as restricting domains, we could go either to the left of the turning point or the right of the turning point. So if you imagine cutting off this entire half, now suddenly all of this passes the horizontal line test and we're happy. Technically, we don't have to even maximize it. We could try to cut off all of that, in which case, again, all of this works out. But what you'll find is that they will typically ask you to maximize it rather than just finding a possible value of the domain. In this case, we're only allowed to touch the upper bound, so we kind of have to be on this side over here. So essentially, we can only cut out all of this. We've got to choose B to maximize it. So our first goal is going to be figuring out where is that turning point, or at least more specifically, where is the X value of our turning point. We have so many ways of doing that. Who can name one potential way we could find that turning point?
You can use calculus.
Yeah, calculus. So you can diff and let derivative equal 0. That's actually how I would always do it. Oddly enough, by the time I got into the exam, that was my default. Derivative equals 0 because, yeah, gradient 0 for the turning point. You could complete the square, which would probably take longer. You could do the axis of symmetry equation, which will be probably similar length to doing the derivative approach. Those are probably the only ways you'd probably consider. If it was in its factorized form, which it isn't, you could just also do the midpoint of your x-intercepts, if you can find those pretty quickly. So a lot of different ways you can find that out. Here we go. I've done the completing the square approach here, and the calculus approach here. Sweet. Now that we've restricted it down to a one-to-one function, we can now properly find the inverse. Worth pointing out though, there's a reason why I've done the turning point form. I've done the completing the square approach here. And it's because if you just start with this function here and swap the x's and y's, trying to rearrange for y in this circumstance becomes quite challenging because you've got a y squared and a y in there. Getting the y on its own, just like it's the exact same problem with getting the x on its own in quadratics. We couldn't just algebra rearrange it. We had to do other methods of trying to get there. So completing the square takes it from having an x squared and an x to just having an x inside of these brackets. One x, one y, So when you do the swap of your x and y location, going from here to here, you're now only having to rearrange for a single variable rather than multiple. So completing the square is pretty much the only way you're going to go about doing this by hand. TechActive will just sort of do this for you. It'll come out a bit messy. So usually these are better off done by hand, even if you do have a TechActive exam that you can use. But okay, so again, we've swapped our x and y locations, we've done our renaming, all we're doing is rearranging at this point. So subtract 9 both sides, multiply both sides by -1. This is squared, so we can do our square root, not forgetting the plus minus, and then finally the subtraction of 2 on both sides. Almost there. Before I move on any further, is it fair enough, like, well, we've had to complete the square here, rather than just sort of try to rearrange the more complicated version? Any questions at all? Okay. Now, this plus minus here is the whole issue with having a not one-to-one function. When you have the plus minus root, you have both the positive part of the root and the negative part of the root. When it comes to functions, we're only allowed to have one of those. So how do we figure out which one we do? That's going to come from our domain and range analysis. So from the beginning, we saw that our domain was going to be from -2 to negative infinity. Right, we had restricted it to that left-hand side. That means that when we do our inverse, that should also be the same as the range. This is our x information for the regular function. That's going to become y information for the inverse function. So we now know that our range of this function now needs to be from -infinity to -2. Hang on, was that right? Yeah, -infinity to -2. And so we're going to do exactly that. Alternatively, you could look at the range of the function that you started with, and then go to and make that the domain of the inverse, which is what I've actually written here. Because sketching this once you know the turning point is fairly trivial. We can see that once you complete the square, because you have to do that anyway, you know the location of your turning point, and since it's a quadratic pointing down, you can also get the range and look at it from a domain perspective. So we know the domain of this has to be from -infinity to 9, so we can do that. Finally, we're going to use that range information to help us out. So we knew that the domain of the original was from -infinity to -2. That means the range of the inverse must be the same thing. Only one of those, plus or minus, is going to achieve this. Since we're shooting off to -infinity, the only way that's going to happen is if we have a negative in front of the root, right? Because positive root, well, doesn't matter what's going on in here, you're only going to have a positive on the outside or undefined. So we've got to have that negative on the outside. That's really all there is to it. I've even done a little bit of analysis here of actually substituting in some values to see what's happening and which root would make the most sense. But even just from a basics point of view, all this being in a bracket, you're either making it positive or you're making it negative. Here's what you get. These are the two portions of the inverse. This is not a function. We need to cut off one of them. That being, we cut off the positive, leaving us with the negative. Any questions about that conclusion? There is one further thing to talk about here, which is the actual language of the question itself. Find the inverse function, f inverse of x. The vast majority of people that see that are just going to give the rule f inverse of x equals this, and that's it. You need both the rule and the domain associated with it. Whenever it says find the function, functions have two parts. They have the rule, which is the actual, like this bit, and they have the domain associated with it. So when it says find function, you've got to give the domain associated with it. If it just said find the rule of the inverse, then by all means, just stick with just stick with this part. In fact, you should stick with specifically that part, because if you give more information, they might start thinking you're just kind of shoving as much out there as possible. We'll see if we can spot both of the, yeah, there you go. Inverse has the rule of this, but you also then got to give the domain associated with that, because it says find the function. Let's see, do they have anywhere where it says find the rule? Not in this one, it doesn't seem. But definitely in the exam, you'll see some differences. You'll see sometimes they say find the rule, sometimes they say find the function. Is it clear enough the difference, what you do, depending on if you're looking for the rule or the function? So let's move on to one of the questions. Let's see, where's a decent place to start? Let's go with something like 3D here. So we have f of x equal to square root 1 minus x, or x is an element of 0 to 1. That is what we're trying to find out inverse of. Find the inverse function, state, domain, range. Cool. How are we going to start this one out?
You can flip the x and f of x positions.
That's it. So x is going to replace that f of x, and f of x is going to replace this x. Nice. What are we going to do from here?
We can make it so that f of x is the subject.
Yep, making this the subject now. So we got it in a square root, so the first thing we would do to rearrange that would be squaring both sides. Then we could add f of x over here. F of x plus x squared equals 1. And then finally getting the f of x on its own. F of x equals negative x squared plus 1. And maybe throughout the whole thing you might want to then chuck in all the inverse notation on it, all of those. That gets us our rule. There's a few other things we have to now do. What's left over?
You have to find the range of the original function.
Yeah, range of original, sure. How do we get our range of original?
You can substitute 1 into it.
Yeah, subbing in.
Yeah, 1.
Yep, 1, sure. So f of 1 we can already see is going to be 0. 1 minus 1 equals 0, and then rooted. Probably do the same thing with, like, yeah, f of 0. So 1 minus 0, 1, square root 1 is also 1. Yes, you can sub in the endpoints. Sometimes there's issues with subbing in the endpoints. Why is there no issue with just going end to end for this function when it comes to finding range specifically?
It only has a negative gradient. Wait, yeah, negative.
Yeah,
Just a
because it's
square root.
flipped, it would have a negative gradient the whole time, yeah. So the key wording around that, if it was like an exam question, which unlikely, would just be to say it's a decreasing graph. It's strictly decreasing the whole time. But yeah, because obviously with graphs that have turning points, you can't necessarily just sort of like here and here, because you're missing this bit of the range as well. So yep, that's going to get us our range. All we're going to do is write it in the order. So range f is going to be 0 to 1. And those are going to be inclusive. Sweet. So why do we need our range of f? What's that going to help us out with?
Domain of it. F inverse of x.
Yeah, correct. It's going to relate back to the specifically the domain of f inverse. So It's just going to come right at the end here, comma, x is an element of 0 to 1. Just copying directly the range of the original is the domain of the inverse. Looking back at the question, it says state the domain and range of f inverse. If it just said find the inverse function, so just the first part of question 3, then this is where we would stop. It does also have that second statement in there, so all that's left is range of f inverse, which we're going to get from what?
The domain.
Yeah. That's it. So x information of the original graph becomes the range information of the inverse. Range, oh, whoops, not like that. Range f inverse is now also 0 to 1. That's pretty much it. That's how these will work every other time. We've already kind of seen a quadratic example. Maybe we could do that. I'm noticing we're getting lower on time. Maybe we'll start playing around with this sort of stuff, because one of the things they love to do with inverse functions is they'll get you to find the inverse, and then they'll also get you to start figuring out like what parameters, so a being the parameter in this case, cause the original and the inverse to start intersecting with each other. It's a very common thing they like to follow up with. And it starts with finding the actual inverse when there are additional variables, or well, more so coefficients involved. So we'll have a look at this question 8. I'll start writing it up. In the meantime, have a think about how you might start it. In fact, it's a very similar graph.
For both of the original graph and the inverse graph is intersect, one of the graph should have an intersection with the line the y equals to x.
Yes, exactly right.
Yeah.
It's a really nice thing that you can make use of, because of the fact that they are reflections across the line y equals x. If we look back at the if I can find it, back at the little picture that I had as an example, we can see these two linears where they intersect is that line y equals x. You're absolutely right. Yeah. So when it comes to finding the intersection point of your inverse and original, you don't even necessarily need the inverse sometimes. You can just work with the original, equate that to y equals x, and then maybe further refine your answer after that. Because what you'll find sometimes is you'll get two solutions to this, and maybe only one of them is valid, depending on where the inverse is likely to be. For linear, that's obviously not going to be the case. That's totally fine. But for other functions, you might run into some more trouble. Like this one probably specifically, because the inverse pair of the root is going to be the quadratic. And as we said before, we only really want one of those halves, not two. So you might still need the rule of f inverse, especially since 8a is telling us to do it. But for now, actually, you might even still... It is also a bit differently here as well, because you'll still have... You now know where they intersect, specifically at x equals 1. So we might still need this. But anyway, so we know that they're going to intersect at x equals 1, which also means they intersect at y equals 1 as well. Because when you're intersecting along the linear, y equals x, if x is 1, y is 1. So you kind of already know that ahead of time now. They're going to touch at 1, 1. Which kind of means it's going to do something like this then. That'll be the root, since it's reflected backwards. Which means we would expect... I'm always so bad at drawing these. The quadratic to do something like that. Yeah. God, that's awful drawing. Just trying to reflect that in the line y equals x. So we probably expect us to do something like that, where that would be 1, 1. And we're trying to figure out under what circumstances do we have that crossover. So we can tell that in this case, since A is our horizontal translation, or more specifically, actually, yeah, it would be exactly A. Let me think about that for a sec. Flip it out, x minus A, yeah, A is going to be the location of the horizontal translation. We got to figure out under what parameters does this crossover actually exist. You can actually do this graphically, based on this little picture. What kind of restrictions on A, as far as domain is concerned, would be required such that we have a crossover?
I don't think we need one.
Say again?
I don't think we need one here.
Don't think we need one. As in A equals 1 is invalid, are you saying?
Wait, what was the question again?
So if we have a look back at like 8b, it's telling us the graphs intersect at x equals 1, find the possible values of A. Well, I guess I kind of made up my own question then, didn't I? Because that's a bit different. Basically, I was going to the more exam-y style question, which would be, you've now got these functions that are crossing over. What values of A would allow them to continue crossing over? So what are all the possible values of A such that f and its inverse would cross over? Pictures like this can help quite a bit.
So 0 to infinity.
0 to infinity, that's right. So if your A is all the way at 0, you have this, and then you have this. You're crossing over at the origin now. If you have any other positive number, then you basically just have this, but you just replace this number with whatever the number is. Absolutely. As soon as you cross over to A being negative, you now have this sort of thing going on. Because again, you're just swapping the location of the x and the y. These are no longer going to meet anymore. This is the kind of stuff you've got to do in the exam. The example in the textbook was a bit easier because you're actually told a specific point they intersect in, and then all you got to do from there is work back towards figuring out what A would have to be under those circumstances. So is it fair enough then how that's worked? I know you came up with it, of course, but this is the kind of thing you'll do. Maybe if it's more complicated, like I could probably pull up a 2024 exam. Surely it's going to have something similar to this in extended response, just so you can see an example of what that would look like. Maybe I went too far. Okay, maybe not. I'll try one more. If not, then I'll just move on. I remember a funky one that had like logs involved. They like to do the relationship between logs and exponentials. Actually, wait, I think I might know. It was a relatively recent one. Maybe it's 2023. Yeah, there you go. Look at that nonsense. So here's your function. You got f of x, which is a addition of exponentials. G is just more or less the same thing, but it's just a bit transformed, been shifted and translated and such with dilations. And basically what you end up with is this. So you got the original in bold, and you got the two inverse pairs of it, one being the positive quote unquote root, and one being the negative root. Because if you look, they're not quite, because it's exponentials. It's not quite a parabola, and so that would not quite be a root. And part of what you have to do in this case is just like we did in the beginning, which is saying, well, okay, finding the inverse of this. The CAS, I believe, just sort of throws a fit. Let me see. I wrote solutions to this. Pretty sure the CAS did not like it. Did I say? Yeah, okay, I didn't really say. But point being, we're just making use of the fact that we already know G. G is a nice and easy thing. And as far as where it's going to intersect, well, as you can see again, both the dotted negative part of the root and the solid positive part of the root both intersect that bold original graph on that line y equals x. So we cut corners by just solving for where those would cut. The corresponding y values, again, it's a line y equals x, so they're going to just be identical. And if you forget that, that's still fine, right? You just shove it back into the original function and you just get the same value back. Now from there, we're talking about like area bound. We're not going to worry too much about that right now. What was more interesting here is now this. So basically, there you go, a log with a root on the inside. Nasty, nasty. Basically, it's the same thing, right? What's the smallest value of k such that we will touch or cut the inverse? So again, we're making use of the fact that it's going to, rather than knowing what the inverse is, we know that it has to touch the line y equals x. So we're making use of that instead and trying to figure out what's the last possible point that they would touch. That's where it starts. You start playing around with the CAS with this sort of thing. So all I'm done is chuck this directly in there. That gets you the C of x. I think, yeah, it should be the C of x there. And then from there, just sort of play with it, right? It's kind of hard to see what k is actually doing here. It's got some dilation elements to it, but it's also got a vertical part to it. And so when we play with it, suddenly we realize it's kind of shifting like diagonally down to the right. And at a certain value of k, it's going to just be on that boundary. This is going to be a bit advanced, but just for FYI for later, basically all I've done there is when it's just touching the line, that's another way of saying I want to make the line y equals x tangent to my function. So that's a nice little coming full circle with the lesson, going right back to the tangent line related stuff. Because the line y equals x, that is a gradient 1, therefore the derivative of our function must therefore equal 1. Figure out where that is, and then just sort of work it from there, basically. You're going to get a couple different solutions in this case. We know just based on our graph that we only exist in this positive region, so we're going to ignore the negative portion of that. And then just go right back to saying, well, okay, making sure that function actually now equals x. So part 1 was making the derivatives work out well for the gradients to work out. And then the next part was now using that restriction of what x actually is in terms of k. This is a nice little funky thing you can do. This isn't just domain, it's just setting parameters for your for the variables in your solve. So you can actually use this to directly replace x with something rather than giving it a domain. And you can also, on top of that, put a... You got a fair bit of freedom with how you... with additional things you can put on this solve. So you can set variables to be certain things, and you can work with another like domain related thing as well. So yeah, if you're curious about like following up that sort of thing, that's probably the hardest by far that inverse functions will start getting, which is they'll give you something that there's no way in how you're getting the actual, well, they're giving you the inverse here. There's no way in how you're going to make the two things equal to each other. This is the 2023 exam 2. You'll be able to see the solutions to this in the exam solutions tab in the classroom. This will be a nice one to revise if you're finding, where is it? Got too many things open. If you're finding the textbook ones not nearly as challenging, well, this is where you would go to start having a look at more complicated things. It's fairly common too. So that was just one example. I feel like they come up every second year or so. They're not too rare, so it's a good one to get good at. That's more or less about it. I don't know where else we could go from that. Is there any final little quick things I should clarify further? Do we need more practice on the fundamentals, or are we all good? Cool. Maybe we'll just finish this one up then. We'll do the actual proper solution to this. So if we go back to what we had, right, it was the two functions intersecting at x equals 1. Find what a would have to be to make that work. So if they intersect at x equals 1, where can we potentially start going to start figuring out what a would have to be? Also tied up our where we're at as far as the working out's concerned. So the picture that's on the handwritten notes bit is pretty accurate to where we're up to. Okay, well, we know the intersection point is going to be at 1, 1. All that's left to do is figure out how we can get an equation that also now has a involved in it. So if we just shove in x equals 1, y equals 1, sounds pretty plausible to me. Right, we've got the y, we've got the x that are located there. So if we place our y equals 1 and our x equals 1, excuse me, that should be all we need, because we know it's going to be at 1, 1. Again, it's along the line y equals x. So even though we were only given the x equals 1 portion, we can infer the y equals 1 will come right with that. 1 squared is 1, a equals 2. So we know that should now be at 2. What's a bit concerning to me is they've said possible values, plural, for a. I can't imagine why there would be any other possibilities, because a is just a horizontal translation. That's all it does. So as soon as you shift it any more right, it'll cut higher up. Any more left, it'll cut lower down. And if you go negative, well, we already explored that. It's just going to keep ascending left, and it'll just have no solutions at all. That's a bit confusing. Possible values. I'm just going to quickly double check the answers for that one, just to make sure I haven't missed anything crazy. Unless anyone can spot something stupid that I've done. 5G. A equals 1 and a equals 2. How can that be? They've gone at it from the approach of equating the root to the quadratic that you would get after doing your inverse. Does that actually work? Because if I do a equals 1 in this, f of x, so square root 1 minus x. That's for a equals 1. Does the point 1, 1 exist on this? 0.11 can't exist on this. So why are they saying that a equals 1 can work? You shove in x equals y and you get y equals 0. I think they've actually stuffed up. Because what they've, I'll change over the screen share so you can see what I'm looking at. I think what they've done is they've fallen into the problem of the quadratic not having a domain associated with it. So remember that this root only comes with the positive portion, whereas the quadratic, when you do your inverse, it has to only have one of the halves, otherwise you're not doing a proper inverse pair. So what I think's happening is they're treating this root as like, well, more so they're treating this quadratic as having both halves, and then the math is coming out such that probably finding the intersection of the negative part of it rather than the positive part of it. That's what I imagine is happening there. Because it's pretty clear, if you shove an x equals 1 here, the 0.11 does not exist on it if you have a equals 1. So I think they've actually made a mistake here. Fun. So something to avoid, even the examiners or the people who wrote this textbook. I'm going to look real stupid if there was actually no issue, but I'm pretty confident there's no issue. Anyway, anything to clarify further? If not, I'll let you enjoy the rest of your day.
Thanks. Have
No
a
worries.
good day.
You too, mate. Take care.